The
The
passive
passive
seismic
seismic
experiment
experiment
produced
produced
several
several
important
important
scientific
scientific
results.
results.
Knowledge of
Knowledge of
lunar
lunar
interior
interior
structure.
structure.
Like the Earth, the Moon has a crust, mantle, and core. The lunar crust is rich in the mineral plagioclase and has an average crustal thickness of 50 kilometers. The lunar mantle lies between the crust and the core and consists mostly of the minerals olivine and pyroxene. The core is probably composed mostly of iron and sulfur and extends from the center of the Moon out to a radius of no more than 450 kilometers, i.e., the core radius is less than 25% of the Moon's radius, which is quite small. In comparison, the Earth's core radius is 54% of the Earth's radius. However, the size of the lunar core is not well constrained by existing seismic observations. Better constraints came from the laser-ranging retroreflector and magnetometer experiments. Distribution of lunar seismic sources. More than 1,700 meteoroid impacts were recorded by the seismometer network, with impactor masses estimated to be between 0.5 and 5,000 kilograms. Most moonquakes occur at depths of 800 to 1,000 kilometers. These occur at monthly intervals at about 100 distinct sites, indicating that these moonquakes are caused by stresses from changes in lunar tides as the Moon orbits the Earth. These moonquakes are quite small, mostly with Richter scale magnitudes less than 2. The amount of energy released by earthquakes in a typical year is about 10 million times larger than that released by moonquakes in a year. Only a few near-surface moonquakes were detected. Attenuation of seismic waves. Meteoroid impacts cause heavy fracturing in the upper 20 kilometers of the lunar crust. These fractures in turn cause scattering of seismic waves in these regions. Below 20 kilometers, seismic wave scattering decreases as a result of either closure of these fractures due to increasing pressure or of a change in chemical composition of the crust. In the mantle, seismic waves are attenuated much less on the Moon than they are on Earth. Seismic wave attenuation is enhanced at high temperatures and in the presence of water, and the low attenuation on the Moon indicates a cold, dry interior. Because the Moon is smaller than Earth, it is expected to have cooled more rapidly, producing a cold interior. The total absence of water on the Moon is due to its formation from dry volatile depleted material, a consequence of the impact of a Mars-sized body with the Earth. Below 1,000 kilometers depth, seismic wave attenuation increases, possibly indicating the presence of a small amount of molten rock. Scientists hope that moonquakes and meteorite impacts would answer two fundamental questions. 1. Does the Moon have a molten core? And 2. What is the deep interior of the Moon like? To answer these questions, they needed at least one impact event of at least 1,019 ergs on the far side of the Moon. On May 13, 1972, a near-side event with an energy of 1,100 kilograms was recorded. On September 19, 1973, a large backside event with an energy of 1,018 ergs took place. On July 17, 1972, only 3 months after it was set up, Apollo 16 seismometer registered the largest impact ever recorded on the Moon when a meteorite hit the far side of the Moon near Mare Muscoviense, located at 26 degrees north 147 degrees east. Over the 8 years of the ALSEP's lives, around 10,000 moonquakes and 2,000 meteorite impacts were registered by the seismometers. The seismic information, magnetometer, and heat flow experiments contributed the principal information about the Moon's interior. It is now believed the Moon's crust is multi-layered and 50 kilometers thick, with a secondary boundary occurring about 20 kilometers under the surface. The upper mantle has been determined to consist of olivine or olivine pyroxene matter, and to be quite homogeneous, extending about 500 kilometers down. Below this level, the seismic data infers the interior is iron-enriched, although there is insufficient data to determine if the Moon has a molten core. Moonquakes were discovered to show periodicity and recur at several places in the interior. The time cycle of the deep focus moonquakes follows the tidal cycles so closely it appears likely that tidal forces are a major factor in triggering deep focus moonquakes. The Moon rings like a bell when struck by a large object. The first man-made crash directed at the Moon that could be detected by a seismometer occurred after the Apollo 12 astronauts had returned to the CSM and the LM ascent stage was sent smashing into the Moon's surface. The shock waves of this impact surprised the scientists. The Moon vibrated for over 55 minutes. Also, the kinds of signals recorded by the seismometers were utterly different from any ever received before, starting with small waves, gaining in size to a peak, and then lasting for incredibly long periods of time. A seismic wave took 7 to 8 minutes to reach the peak of impact energy, and then gradually decreased in amplitude over a period that lasted almost an hour. It was claimed that even after an hour, the minutest reverberations had still not stopped. When the Apollo 12 LM hit the lunar surface at 6,048 kilometers per hour, 72 kilometers from the landing site, digging an estimated 9-meter wide crater, the results were astonishing. All 3 seismometers in the package recorded the impact, which set up a sequence of reverberations lasting nearly an hour. Nothing like this had ever been measured on Earth. The LM impact occurred at 1617 USCST November 20, 1969. A news conference had been scheduled to begin at 1630, and when it did start, the Moon was still ringing as the scientists, all of them seismic experts, arrived at the news center from their laboratories. Maurice Ewing, co-head of the seismic experiment, told the afternoon crowd of the unexpected event, informing them that the Moon was still ringing. He confessed he was at a loss to explain why the moon behaved so strangely. As for the meaning of it, Ewing announced, I'd rather not make an interpretation right now. But it is as though one had struck a bell, say, in the belfry of a church a single blow and found that the reverberation from it continued for 30 minutes. As he spoke, the reverberations continued on for another 25 minutes. Dr. Ross Taylor, a lunar scientist who had been on the team to examine the Apollo 11 samples in Houston, explains why the moon rang for so long. This was one of those extraordinary things. When you had the impact of these things on the moon, unlike a terrestrial earthquake which dies away quickly, the shock waves continued to reverberate around the moon for a period of an hour or more, and this is attributed to the extremely dry nature of the lunar rock. As far as we know, there is no moisture on the moon, nothing to damp out these vibrations. The moon's surface is covered with rubble, and this just transmits these waves without them being damped out in any way as they are on Earth. Basically, it's a consequence of the moon being extremely dry.